Hello, we're the UNH LunaCats, and what we are is we are a multidisciplinary team consisting of engineering students, computer science, and business students. This is our 9th year competing, with previous years having success with getting 3rd place and 5th place. And for this year, we've decided to focus our design on the drivetrain, the wheels, the chassis, the electrical system, and the autonomous controls.
So in this robot, we have 4 main safety features. The first of which being an easy, accessible emergency stop that will end all functions and processes on the robot. We also have limit switches to prevent the auger from overextending. We have a custom conveyor and custom cover for the conveyor and the motor gears to prevent dust and other things from getting in the gears. And we also have circuit breakers to prevent overcurrent.
So with this robot, we have multiple risks we had to take into account, along with plan and how we would control those risks. We had a severity level of 1, 2, and 3, where 1 is not as severe, 3 is the maximum severeness, which could lead to mission failure. The first hazard we noticed was project incompletion with a severity level of 3, where the team planned on avoiding this by meeting late nights, working hard to make sure we stay on schedule. The second is wheel failure. Extra wheels will need to be brought to the competition to prevent this from causing a severity level of 3. Motor failure is another hazard. We plan on avoiding this by testing stresses, which we had done, and having motors brought with us to competition. Chassis structural failure is another, along with communications failure and power failure.
Okay, so when we're demonstrating the robot, we're also demonstrating the safety plan. In order to make sure that everyone is safe while we're demonstrating the robot, we're trying to use the remote control, limit the use of the auger, and also observers will stay at least 2 feet from the robot while it's activated.
So the project and system performance goals are split into 3 categories: physical, mechanical / electrical, and operational. One of the physical requirements was for the robot to weigh less than 70 kilograms and fit within all the size requirements. A mechanical and electrical system performance goal was to be able to overcome obstacles the robot encounters on the course, and also to get out of a ditch without popping a circuit breaker. An operational system performance goal was to receive sensor information to the robot every 2.5 seconds to reduce bandwidth.
Our design philosophy was to build a robot that would qualify for the competition by meeting all of the NASA requirements and mine at least 1 kilogram of icy regolith from 30 centimeters under the topsoil. One of our goals was to minimize the costs and weights by avoiding materials that were expensive and that were unnecessarily heavy. Our big improvements from the previous year were to enhance the drivetrain, use a better wheel design, and redesign the chassis, as well as implement autonomous operation.
So one of the analyses that we did this year was on the mining functionality of the robot. So after last year, we realized that the auger and conveyor mechanism was very efficient at digging and was actually one of the best. So we decided that we wanted to keep it and try to improve upon it. So what we ended up doing was we moved that from the last year's chassis onto this year's chassis, making minor changes. One of the biggest changes that we did make, though, was to the actuators. Last year, one of the things we noticed was the actuators weren't synchronized correctly, so one side would actually raise and lower faster than the other. So what we did was we bought new actuators and readjusted everything to make sure that the auger would raise and lower at the same rate on both sides to prevent any mechanical failures.
One of the first alternative designs we did for the robot this year was to get rid of the old rubber wheels that you can see in the top picture. These wheels seem to not work so well in the competition, in the sand, and the terrain. we decided to change those into more lighter, deformable, and hollow wheels that you can see in the bottom right picture. 3D printed wheels were also an option we considered, but due to time, we decided to go with the wheels that you see.
Another alternative analysis component was the wheel mount. We initially decided to go with the spring-loaded pin, but later decided against it. It was too complex and had too many precision components. We eventually decided to go with the milled rod that would be screwed into the wheel and connect the motors. This was more reliable and feasible, and it was initially not considered, but heard of from another senior design team at our university.
So our design process this year was to first design the wheel mount in SolidWorks, which we had milled out using a CNC machine on campus, and it's made with aluminum stock. We also designed the chassis in SolidWorks and had it made by an outside welder. The wheels are mounted with the CNC screw plate. New actuators were installed to extend the reach of the drill, and we attached those to the robot. We also made a conveyor motor cover, which was designed with SolidWorks, and we 3D printed it on campus.
Final design for the drive portion of the robot included three main aspects: the chassis, the wheels, the drive, and the drivetrain. Chassis is made out of hollow aluminum 661, which had a low cost and density but a very high durability. The wheels, as stated before, were kayak wheels. They're designed to deform and compress to the terrain, increasing surface area and increasing traction, and they were modified to securely attach to each of the axles. The drivetrain included 4 VEX bag motors with a 100-to-1 gearbox ratio for each of the wheels. The axles were specially designed and built to connect each motor to each wheel, and motor mounts were also designed to connect and keep each of the 4 motors stable.
The final design for mining, so the first component that we use is the auger. The auger is driven by an ion motor and was actually disassembled from an ice auger that was bought off the shelf and repurposed to use for our robot. This auger is raised and lowered with actuators that are lifted with ball screws on the sides. This allows the auger to go down into the dirt, digging up icy regolith and simulant, dropping it onto a ramp that leads to a conveyor belt. Along with the auger, we have 2 actuators that raise and lower it. Those are powered by a 12-volt battery voltage system, and they have a capacity of 150 pounds speed load. Lastly, we have the conveyor belt. This is driven by a small motor with a gear system. This allows us to deliver the icy regolith from the auger to the collection bin when we get back to the deposit area.
On the electrical side of the robot, we have 2 batteries, a 12-volt which powers the majority of the robot, and a 40-volt battery which powers only the auger. We also have 2 electrical boxes. The one you can see here is the power box, which contains the power relay, the power controllers, the emergency stop button, and the circuit breakers, which protect the robot from overcurrent. We also have a control box, which includes the Raspberry Pi and the Arduino, which run the autonomous program, and the display monitors, which show how much power is being used.
So the wheels were tested on the bottom left picture on a rig frame we set up in order to see how it deformed to the surface, along if it would support the weight of the robot and avoid the obstacles. The wheel axes, shown in the middle picture, was tested using SolidWorks to determine the stresses that would be occurred due to the weight of the robot. Autonomy was also tested using the test rig on the bottom right.
Okay, so in order to make the robot fully autonomous, what we've done is we have put a Pixie camera on the back of the robot in order to see the placard. And we have also positioned 4 lidars next to the wheels. These lidars are meant to detect obstacles and also holes in front of the wheels to allow the robot to turn to avoid them. And the Pixie camera is going to be used to determine the robot's position in the field. This will allow us to be able to navigate the field safely and know exactly where we are at all times. If this doesn't work during the competition, we can also take control of the robot manually. This will allow us to basically, we can use a remote controller to actually send instructions to the laptop. The laptop can then send instructions to a classic server running on the robot. The robot can then execute the instructions and send back a status of how it's doing to the laptop, which will be running a Node.js server. This is how we're managing communication over the network. Basically, additionally, if we need to test any of the features later on, we're storing all of the information we get from the robot and also all the commands we're sending it on the MongoDB server running on the laptop. This will allow us to also test it in a virtual robot field simulator that we have created.
So this year we decided to change up the drivetrain, which instead of going for 2 motors with chains, we went to 4 motors with gearboxes, and these gearboxes help to increase the gear ratio, and the new motors help to increase our torque. We also went from the old solid rubber tires to these new kayak deformable tires, so that they reduce weight and they offer more traction due to the ability that they can deform to the terrain. And then our big thing that we focused on this year was the autonomy, which we did by adding some sensors to track the location of the surroundings and a camera just to monitor the entire field.
So for future improvements, we have laid the groundwork for the autonomous code to be improved upon, as this is our first year attempting to have the robot run fully autonomously. We have also laid the groundwork for a better sifter and auger mount. We will also be leaving behind $5,000 for a starting fund for the next year's team to allow them to buy their parts earlier and not have to worry as much about their budget for the next year.
So the purpose of our project management is to monitor the team's budget, schedule, and risk. Our faculty advisor is Professor Maywin Thane. We also have 2 graduate advisors, Jesse Fang and Matt Westbrook. Nate Tetro is our senior project lead and CEO. And we also have drivetrain, chassis, electrical, and programming leads, as well as organization leads, Chief Financial Officer Ashley Apostolos, and social media and outreach.
So for our budget, majority of it comes through the department, but we also get some funding through grants and sponsorships. And all of our income that we spend ends up taking out of the senior project budget and gets reported to the CFO to make sure that everything is accounted for and that we have enough money in the budget to keep the robot running.
As you can see, this is our team schedule. It has dates including one to order all the parts by, one in which we wanted to have the first iteration built by, another for the competition days, and finally for the project completion date, in which the project has been passed off to the underclassmen and the robot has been unpacked at UNH. Lastly, this is our schedule for the NASA deliverables. Again, we have all those 4 dates, but we also have a schedule for when we plan to work on the project systems engineering paper and other deliverables like that.